Hello and welcome to this instruction on variables and formulas. We start with variables, the alphabet. How did that end up in mathematics? Perhaps you've heard parents or friends or other math students say, oh, math was just fine until we got to the alphabet. Why did we put that in there? That was horrible. Well, the answer is because we're humans. We're above the beast. We have abstract reasoning. We start with something, a very simple word, perimeter. This is actually two words. It's a prefix, peri, meaning around, and meter, meaning measure. So let's say we have a rectangle over here. That's a nice little guy right there. And we have 3 inches and 8 inches and 3 inches and 8 inches. If we want to measure this thing around, we can actually go and do it by an arithmetic. We can say, oh, that's 3 plus 8 plus 3 plus 8, and walk all the way around it. And if we do another one, well, oh, that'll give us an answer, won't it? 6 and 16, that's 22, say, inches all the way around. Well, this one, what if it's 2 inches and 11 inches? Then we're going to do 2 plus 11 plus 2 plus 11. And we start to realize that there's a pattern to how we get the perimeter in a rectangle. And so we say the pattern is that we take the width and then the length and the width and the length again. And this right here becomes the pattern by which we can solve every single perimeter problem as it pertains to rectangles. And we just use these variables, W plus L plus W plus L. And you guys have seen this before, and say 2 L's and 2 W's. That's great. But look at what we did. This letter allows us to set the pattern for any number of numbers that go in for it. So that's why it is a variable. And it allows us to exemplify and write out what the pattern is without knowing what the numbers are for any particular situation. And that brings us to this next one. Formulas. You know how cool formulas are? Formulas are the patterns, better write that down, they are the patterns by which we solve these different problems. As an example, let's say I had 13 quarters, 7 nickels, and 2 pennies, and I wanted to find the total value. Well, yeah, we'd take 13 times 0.25, 25 cents. We would take 7 times 0.05. And we would take 2 times 0.01, 1 cent. We're like, okay, 13 times 0.25, what does that equal? Well, that would give us 3.25. 7 times 0.05, that's 0.35. And that's 2 cents right there. So we end up with $303.62. There we go. Now, we would do this over and over. So what if we didn't know the number of quarters and nickels and pennies? Could we still write down the pattern? Well, yeah, this is what a formula is. Somebody's already gone through all of the work. And the value of this would be 0.25 times however many quarters we have, plus 5 cents for every nickel, and 1 cent for every penny. And if you had dimes on there, it'd be 0.10 times the number of dimes. Look at that. We're mathematicians. We just made up a pattern, and we could hand this to all of humanity, and they would be grateful forever that we did it. Another one that we can make up, another one that we can do is something as easy as, well, distance, rate, and time. Let's try that. If you drive 30 miles per hour on your bicycle, and you do that for 2 hours, so here's your rate, here's your time, and what's your distance? Okay, distance, rate, and time. Well, 30 miles per hour. If you do that for 2 hours, that's 30 miles the first hour, 30 miles the second hour per hour, 2 hours, you end up with 60 miles. And you look at that and you're like, oh, did you really just times those two? Let's say you were driving a car 70 miles per hour, and you did that for 3 hours. Well, 70 miles per hour. So 70 miles for the first hour, second hour, third hour. You end up, yeah, timesing them, you get 210 miles. You're like, wait a second, can you always take the rate times the time and equal distance? Does that always work? Yeah, rate times time equals distance. We stop here for just a moment to realize that the x that was always used in arithmetic was replaced by a dot, because now that we can use the alphabet in math, x gets used for a variable instead of a symbol of multiplication. So the dot will replace the multiplication symbol, or putting things exactly next to each other will also do that. Notice that this is then a pattern. If you always follow this pattern, you will always get this correct. If you take rate divided by time, you won't get it right. If you follow these patterns that formulas provide for you, you will always get the correct answer. This has a fantastic spiritual connotation, and I'll let Elder Ashton tell you about that.
Over the years, I've experienced some uncomfortable times in commercial aircrafts while traveling in turbulent skies. Oftentimes, heavy winds, storms, angry clouds, downdrafts, and so on have caused bumpy and anxious moments, particularly when it was time to land. A seasoned pilot gave me comfort once after such an experience when he talked about a landing pattern, the ordered flight path of an aircraft about to touch down. Precise instruments, experience, and trust guide the planes to safety en route and through proper landing and takeoff. We can't control the weather or elements, but we can stay within the pattern for safety, he emphasized. One day I was admiring a beautiful hand-finished quilt made by a skilled seamstress. As we visited together, I learned that she had made many quilts over the years and was well known for her excellent handiwork. To my query, "Do you ever make one of these quilts without a pattern?" she said, "How would I know how it would turn out if I didn't have a pattern to follow? How can we even guess how our lives will turn out if we don't choose to follow the right pattern? What a happy circumstance and strength in our day to have the Lord's promise, 'I will give unto you a pattern in all things, that ye may not be deceived, for Satan is abroad in the land, and he goeth forth deceiving.'" I have always received courage, comfort, and direction from that powerful quotation. A pattern is a guide for copying, a design, a plan, a diagram, or a model to be followed in making things, a composite of traits or features characteristic of an individual. It is also the ordered flight path for an aircraft about to land. The gospel of Jesus Christ is God's pattern for righteous living and eternal life. It makes possible goal setting and lofty priorities. Satan and his advocates will constantly try to deceive and entice us into following their patterns. If we are to achieve daily safety, exaltation, and eternal happiness, we need to live by the light and truth of our Savior's plan. All salvation revolves around our Savior. In a recent conversation with a drug addict about priorities, life's patterns, hopes, goals, and purpose, I was grieved when this attractive young lady said, "God is loving, God is kind, leave me alone and never mind." The wayward and the disobedient will never be happy while smothered with Satan's suggestion that practice makes permanence. God's gift and commitment to agency never will include a tolerance of sin. God is truly loving and kind. Part of his pattern is to help us use our gift of free agency, but his pattern does not condone sin. When we abuse our agency to choose a lifestyle contrary to revealed patterns, we must live with the consequences. Our unwillingness to follow the true and tested patterns given to our happiness causes the individual, family, friends, heartaches, and ultimate disaster.
Though certainly not as hefty and as far-reaching as the patterns that he was talking about, the patterns in math will lead just as surely to your success or lack thereof. So let's get back to the math. All right, let's go through one final pattern formula, as mathematicians call them, on how to solve problems, and then we'll give you an opportunity to do some on your own. So let's say you had something like $62. you go and you see it on sale, $62, but it is indeed on sale for 35% off. You're like, oh, we can do this. We know what percents do. If you take 0.35 and you times it by 62, that will tell you how much money you saved. 0.35 times 62, what is that? $21.70. Now notice it was 35% of this original price that came off. So that needs to be subtracted from the original $62. And what does that give us? $40.30. Oh, that's nice. Look at that. 62 minus the 35% of 62 off, meaning we subtracted $40.30. Notice that if this is our original price and this is our rate, and here's our final price, we have just created the pattern by which all of these problems can be solved. Price minus rate times price is going to equal our final. If it was a tax or a markup, this thing would be a plus. So now, here's a chance for you to do some on your own. To the boards! So here we go. Here are 4 problems. A temperature conversion, the formula's already been given for you. Percent increase, notice we have a plus sign here. A distance rate time problem, and a compound interest. This is if you start with a certain amount and then compound it at an interest rate for a certain number of times, in this case monthly, for 20 years, how much money, what is the final amount? These formulas have been provided for you. Go ahead and stick these numbers in and see if you can get the answers. Go ahead and pause the video and press play when you're ready to go again. Oh good, I hope you had a chance. Here we know what the F is, and so we stick the 86 right up in there. Somebody's already done all the thinking for us, so now we know that C is 5/9 times 86 minus 32. Order of operations, we take care of this first. 86 minus 32 is 54, so we get 5/9 of 54. 54 and 9 will cancel, leaving a 6 and a 1, so we get that C is 30. And this is actually correct. This formula is transferring Fahrenheit into Celsius. So 86 degrees Fahrenheit is 30 degrees Celsius. So we would write 30 degrees Celsius. Excellent. So here, 52 is the P, and this, when it goes in, make sure you know that that is a 0.07, 7%. You must move the decimal 2 places, and the 52 goes for the P there. So we get 52 plus 0.07 times 52. And what does that equal? F equals, punch that into a calculator, 55/64. That's exactly right. Distance, rate, and time. So we know that the R, 5.3, goes right there, and the T, which is 7, goes right in there. So we have 5.3 times 7 equals our distance. Distance equals, and we get 37.1. Miles, kilometers, I'm not sure what that is. All right, the next one, 2,000. 2,000 goes in for P. Now remember, this one is a percent, so when this goes in right there, this is going to be 0.072. N is 12, so that will go in right there and right up there. And then the number of years is going to go right there. And this will give us the final amount. This is a pretty big, tough thing, so let's pull up a calculator and stick it in so we can all see it. As we write it out, A equals 2,000 times 1 plus 0.072 over 12, all to the 12 times 20. Here we have a calculator to punch all this in. We get 2,000 times parentheses 1 plus 0.072 divided by 12, close that parentheses, all to the parentheses 12 times 20. Make sure we're okay with that, that 12 times 20 all has to be up in the exponent. And we hit enter, and A equals 8405.15. Round to the nearest penny, and this will probably be in dollars. Now, if you finish these, Congratulations, nice job. Those are the solutions. You'll have those in your video notebook, but you should already realize that when somebody gives you a formula, they have provided the pattern for you. You just need to plug it in. And this right here, if you can say, oh, we have the formula, just stick it in. That is where you want to be. If you can say that, oh, just stick it in. That's all these arrows mean, and that is the whole crux of having a formula and being able to do stuff. Similar to all the formulas that we've had throughout history in solving problems and providing answers to mankind, mathematicians have studied shapes and the formulas that deal with shapes. So notice we could have shapes like rectangles and triangles and circles and cones with a circle down on the bottom. We could have pyramids. We can have rectangular solids, spheres. Let's see if we can draw a cylinder here. Before we talk about the formulas that we've discovered and created to describe certain things, we need to talk about a few things first. So let's put this down here. We need to first of all mention if you have something that is zero-dimensional, that's like pink, a little point right there. And what it represents is just a location. It doesn't have any length, width, or height. Now, if you stretch it in one direction or connect an infinite many of them in one direction, we get something that is one-dimensional. In particular, we can start measuring things that have a length. So it looks kind of like that. And it could be curved like around the circle. A perimeter is something that we measure length in. Circumference of a circle. A distance. So we do that and we get answers in inches, feet, meters, centimeters, kilometers, miles, yards, any of those things. And so these are all appropriate answers when somebody says, how tall is it? Or how long is it? Or what's the radius of the circle? Or what's the side of that rectangle? These are all appropriate ways of answering that question. Now, if you take something that is one-dimensional, a certain length, and you drag it in a certain way, so it creates, or you line up infinitely many of them, you get like a flat surface here. That's like a two-dimensional object. Two dimensions because you can now measure both its length and its width. So it has both length and width. And if it's got both length and width, you can now compute the area inside of that figure. So this one right here, let's say it was 2 feet by 5 feet. You could measure its perimeter, 2 feet and 5 feet, that's 7 feet, plus 2 more is 9, plus 2 more is 14 feet all the way around. That's how you get the perimeter of that. But if you're getting the area, notice 14 feet doesn't make any sense because it doesn't color the inside of it. Notice that the inside is colored by little squares that are feet by feet. So if you have a foot by a foot, what it creates is a square foot. Or we put it like this, a foot squared. So this area formula up here, I think you guys have seen it before, length times width, in this case would be 2 feet times 5 feet. Oops, there we go. 2 feet times 5 feet, which gives us 10 square feet. A foot looks like a piece like that. A square foot is a little patch, a little area patch. And so 10 square feet, you'll notice 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 square feet right there. And so that's what a square foot is. So anytime you're asked an area question, you'll give the answer in square something, like inches squared, or feet squared, or meters squared, centimeters squared, kilometers squared, miles squared. And this squared designates that it is answering a question for 2D. Now notice not everything is flat. We have 3D objects. And what's so cool about 3D? They pop off the screen at you. It's really cool because now we're measuring things. Well, let's take this guy and stack infinitely many of them on top of each other, and we now have a 3D object. Look at that. Oh, that's a beautiful little thing, a cube type thing. It has 3 dimensions, meaning it has a length and a width and even a height or a depth to it. Yeah, there we go. And it allows you not just to find the area on the outside of this, but you can now fill it up on the inside and you can find the volume. So just like we had before, this would be, let me see, a foot by a foot. And now we stretch it up through another foot. And this right here would be a foot that makes a cube or a cubic foot. If you did that with a centimeter, it would be a cubic centimeter, which is abbreviated cc, by the way, and is used to designate the volume of an engine, the size of an engine, 500 cc's, 800 cc's, or medication. If you take 20 cc's of a certain medication, that would also be used there. It could be yards cubed. That's how concrete is measured, by the cubic yard. Meters cubed, miles cubed. Anyway, you'll notice this 3 here will always designate that you're answering a 3-dimensional question. So when you get the formulas, and they're in your book for rectangles and triangles and circles, mathematicians have studied it for years and years and years to illustrate the patterns that will always give you the exact number of square patches for area, cubes for volume, and they don't always come out to be even numbers, but they will help you. Another note, they studied circles for a very long time, and they would measure them straight across and then all the way around. And they're like, wow, going all around is about 3 times the size of going across. And no matter how big the circle was, it could be this big or it could be miles around. And whenever you divide it, it was always just about 3 times bigger. A little bit more than that. It was, and you start recognizing this number, you're like, wait a second. Yes, that is where the number pi came from, is they would measure around a circle and then measure straight across a circle and divide those 2 numbers. That's where we get this, that the circumference is always 2 times the radius times that number pi. And so that's the relationship between the radius and the circumference always. And you will always find that to be true. The area of a circle, again, uses that number pi. So you will see pi r squared, 2 pi r. It will show up in cylinders and cones and spheres all the time because it is the common ratio of a circle to its diameter, or twice its radius. So there are some formulas provided for you in the book. Let's go to the boards and practice a few. To the boards! Here are 4 problems: the cylinder, the cone, the rectangle, and the triangle. The formulas are in your book in section 1.3. But we'll list them out here and then give you a chance to try them on your own. For the lateral surface area of a cylinder, it is 2 pi r h. And remember, this is area, so your units will be in inches squared. For the cone, the volume is pi r squared over 3, or times by 1/3. For a rectangle, the perimeter is 2 heights plus 2 widths, or 2 lengths plus 2 widths, and you'll be able to do that one. And then the triangle, the area is 1/2 base times the height, or base times height divided by 2. Okay, give it a chance, plug those in, and see if you get the right units as well. All right, now that you've unpaused the movie, let's make sure you did these right. So we stick in the R for the 7 inches for the radius. Let's put that'll go right there. And the 13 for the H. So we have 2 times pi times 7 times 13. 13 times 7 is 91, times 2 is 182 pi. So the LSA equals 182 pi. Let's pull out our calculator. 182 times, and you'll notice there is a pi button. If you use 3.14, you'll be just a little bit off, but it's not too bad, nothing to be worried about. And you get 571.08, 571.8. And notice that these are in inches, and we're doing an area, so this is inches squared. Notice that that also works in the formula. If that's inches and that's inches, when we times them, we get inch times inch, which gives us inches squared. Excellent. Here we have a cone. Let's stick it in. So the 5 goes in for the R. And look at that, I forgot to give you part of the formula. I apologize. That's pi r squared h. If you need to pause again to run through again, go ahead and do that. So you get pi r squared h, the 5 goes in for the r and the 12 goes in for the h, and we have equals 1/3 pi times 5 squared times h, which is 12. So 1/3 times 25 times 12, that's going to be 100 pi, which you could do on your calculator if you can see that it is going to be 314.15, so 314.2, and this is volume, so we better be in centimeters cubed, a three-dimensional answer. Notice that this is true when you have centimeters and you square it and then you times it by centimeters again. Centimeters times centimeters squared, we now have 3 of them, which will give us centimeters cubed. Correct. All right, perimeter, 2 length plus 2 width, or 2 height plus 2 width, and we get 3, 2 times 3, plus 2 times 1.7. So the perimeter is going to be 6 plus 3.4 equals, that's 9.4 meters. Now notice the perimeter is just the length around, so it doesn't become meters squared. And you can see that in the formula. If this is meters and this is meters, they're just like terms and they add. They don't times each other and become meters squared. Good. And then the triangle. Area is 1/2 base times height. If you're thinking, shoot, we should just stick it in, that's a really good place to be. You just stick it in. Somebody gave us the formula. That's nice. So the area equals 1/2 times the base, which is 17.2, times 5. I'm going to pull out the calculator for this one. 1/2, which is 0.5, times 17.2 times 5. And we get 43. So the area is 43. Now notice that this was in yards, and we times it by yards, yards squared. Does that make sense with what we're finding? Yes, we're finding area, which better be a second dimensional answer. And there we have area. Before we leave these, there is one final thing. A circle, a triangle, and a rectangle. You will be expected throughout the remainder of your math life to know these formulas: perimeter, area, and the angles in here, and area and circumference of a circle. These are the 3 basic shapes that create all the others. And so you should take some time and make sure you know rectangles, triangles, and circles. Okay, to the last section, translation. In the world of math, we have formulas, patterns, we have solutions, we have everything is solid and arithmetic, and we can do everything over here. Well, the real world over here has some real problems, and many of them can be solved if we translate them and move them into the math world. This is going to be the basis for all algebra. When we take a real world problem and we turn it into there, where we have equations and we have rules and everything we can work with in the math world, it's actually really nice to be able to stick stuff in here. So we need to be able to translate stuff. So we're going to go through and make sure you can translate certain things. So first of all, numbers. Let's look right here. A number can translate to x or y or z or p or q, any variable at all. If it says 2 numbers added together, what does added together do? Oh yeah, that's a plus sign. There are other ways to do it: sum, or increased by, other things that go to plus. There's a whole list of them in your book that will allow you to do that. You can think if it's getting bigger, then it does that. Now what if it says minus? What does that do? This comes over here to subtract. If it's less than, going down, colder, or discount, they will all go to a minus sign. If 2 things are timesing together, like twice as big, well, twice as big, that's 2 times whatever. Twice a number would be 2x. You could have 3 times a number. The official word is product. The product of 2 and 7 would be 14. And then the other one you can do is divide. So if it's 20 divided among 3 people, or 15 out of, ooh, there's a really good one we need to talk about. The word of normally means multiplication. When you have 2 baskets of 5 apples each, you would times that to get the total number of apples. But out of means you have like 15 out of 20 on a quiz. So out of gives you a divide sign. Also here is the word quotient. So this will all go to divide. Notice that this is a fraction bar with a number on the top and a number on the bottom. That's where we get this divide sign from. So all of these are translations. So there's like a language dictionary that will help all of these to come about. Let's give you a couple of opportunities to see how it works and then try a couple yourself. So if we said 2 more than 5 times the height, well, you'd go 2 more than 5 times the height. So 5 times h, we don't know what h is yet, add it onto more than 2. Oh, good. And what does that equal? I don't know. If you have the word is or are or any verb like that, that goes to equals. And then say the width. I don't know. Let's try that. That would then be, oh, we don't know what it is, so that's a W. 2 plus 5h equals W. How about 2 less than 7 times the height? Equals the radius. 2 less than 7 times the height equals the radius. You might be tempted to go 2 minus 7h, but we need to look at this very carefully. In our translation, we need to make sure it's precise for the math world to work on it. So let's try this. What is 2 less than 20? 2 less than 20. If that's your age, that'll be a little bit easy. 2 less than 20? Well, that's going to be 18. Think, what did you do there? 2 less than 20. You actually didn't do 2 minus 20. That wouldn't give you 18. That'll give you like negative 18. So you did 20, and then you went 2 less than that. So notice that with less than, it needs to switch these 2 places. And notice you could do that with more than. You could start with 5h and do 2 more than that and get 5h plus 2. With a plus sign, you're able to switch them around. A minus sign, you can't. So this is actually going to be 2 less than. So we're going to subtract 2 off of 7 times the height would equal the width. Yes, indeed. Less than you have to be very careful with. All right, let's give you a chance to do some on your own. And one more time, pause the video, look at these problems, try to do them, and then press play when you're ready to go again. It says Jim has, that's going to be an equal sign, 8 more than, we can just use a plus sign there, twice, which is 2, what Bertha has, so we'll make that a B. So Jim's equals 8 more than twice Bertha's. Good. Let's try this one. You had a chance to do it. Fred's income is 13 less than 4 times Julie's. Fred's income is, there's the equal sign, 13 less than. Remember, less than, we need to switch them. So 13 needs to be subtracted off of 4 times Julie's. That's 4J. Excellent. And that will summarize this section.